Most of us learn that water freezes at 0 degrees Celsius, and in many cases, that's true. But under the right conditions, water can actually stay liquid even below that temperature. This phenomenon is called supercooling, and it shows that temperature alone doesn't fully determine when a phase change happens. Supercooling occurs when a liquid is cooled below its freezing point, but remains liquid because the freezing process hasn't started yet. So what's missing? For ice to form, tiny crystal structures need to develop first. This process is called nucleation. You can think of nucleation as the starting point for freezing. But forming these tiny crystals isn't easy. It requires overcoming a small energy barrier. We can actually describe this behavior more precisely using an energy balance. This term represents the energy required to create the surface of a tiny ice crystal. And this term represents the energy gained from forming the solid phase. The key idea is that very small crystals are unstable at first because forming them requires energy. So until a crystal grows large enough, freezing doesn't continue, and water remains in a supercooled metastable state. The metastable state is a condition where the liquid looks stable but is actually waiting for a trigger. That trigger could be a vibration, movement, or a small particle. Once nucleation begins, the system rapidly transitions into ice. Some real-world impacts can be seen in things such as aviation, where in the atmosphere, tiny water droplets can remain liquid even at temperatures far below freezing. When these supercooled droplets collide with an aircraft, they freeze instantly on contact. This creates ice buildup on the wings. When ice forms, it changes the wing's shape. It reduces lift and increases drag. In severe cases, this can impact flight safety. In nature, some plants survive freezing temperatures by preventing ice from forming inside their cells. Instead, the water stays in a supercooled liquid state, avoiding damage. In engineering, we can see supercooled examples in things such as cryopreservation, where scientists try to cool biological samples without forming ice. We can also see them in thermal energy storage systems, where supercooling can delay when stored energy is released. We can also see it in material processing. Supercooling affects how materials solidify and their final properties. This water has been cooled below its freezing point, but it remains liquid because nucleation hasn't occurred yet. By disturbing it, I'm triggering nucleation, giving the system the starting point it needs to freeze. And just like that, the metastable liquid rapidly transitions into a stable solid.